So much like other DHCP server, whatever it is, when DNS was designed, again when you get these replies, there is no source authentication. Did you get it from the right DNS server or not? There is no authentication. In fact, that is the cause for all these issues. Okay. So let's see what this farming means. Farming is basically an attack where a host name, by the way, DNS doesn't just do host name to IP address mapping, it does lot more things also, but I am just focusing on this because this is something everyone relates to. Okay. So this host name to IP address, if you are maliciously mapping, as in they do not belong to each other, but you have mapped it like this. So host name belongs to some other IP address, but you gave a malicious IP address. This changing this mapping is what is called farming, that is called a farming attack, where you are changing the host name to IP address mapping. Okay. As I mentioned, this is only one thing. You can get what the mail servers for an organization are, all this also you can get as part of DNS. No, so often farming goes hand in hand with something called phishing. So basically what you do is, for example, if you have a bank.com, you will use farming to map this to Mallory's IP address. And on that Mallory's IP address, whatever server, you will have an identical website as the bank. That is called phishing, where you cannot distinguish. There you will enter your username password corresponding to your bank because it looks identical, but that information is going to Mallory, who can then use that information to circumvent certain things. So that is the basic idea. So farming and phishing will go together. So what we are going to now see is how is this farming done in DNS. Okay, so that is what we are focusing on. So I am going to pose a very interesting problem. Let us say there is IIT Delhi, okay, and this is IIT Bombay. IIT Delhi has its own authoritative name server. Authoritative name server means this name server can resolve the host names of any machine that is part of IIT Delhi. If you say IIT www.iitdelhi.ac.in, what is its IP address, this machine will tell. If you ask www.csc.iitdelhi.ac.in, this machine will tell. Okay, so this is the authoritative name server who will know all the mappings of IIT Delhi's machines. Okay. There is some user here who is outside of both IIT Bombay and IIT Delhi, who is accessing some IITB's machine, wants to access, let us say www.iitb.ac.in. So he wants to access this machine. Now let us assume that Mallory has hacked into this. Okay, Mallory has full control over IIT Delhi's authoritative name server. But this user is not accessing IIT Delhi's machines. He wants to access the website of IIT Bombay. Now, is there a way, if this is the situation, that it is sending Mallory's IP address, or rather this is not sending, but when he does it, let me not, this is not send. So this is IITB's access, but when he does this, he ends up accessing Mallory's IP. In other words, he is contacting Mallory's IP to access IITB's website. It's a very weird problem, right? I mean, you are trying to reach out to IIT Bombay's website, but you end up on some malicious website when IIT Delhi's authoritative name server is compromised. So this is possible because of these things called glue records. Not just this, something has happened in this setup where for this to succeed, what had happened was in the past, this user had contacted IIT Delhi, authoritative name server. Okay. Now, this IIT Delhi's authoritative name server has basically maybe given some information to him. Maybe it said maybe csc.iitdelhi.ac.in is corresponding to this IP address. Okay. In addition to that, it could have also given some glue record, and within this glue record it could have potentially said that is Mallory's IP. Remember, DNS was also not designed with security in mind, whatever it is. So, if Delhi's reply had a glue record which had this mapping, the local, whatever this guy's local DNS server will install this mapping by parsing the glue record. It does not care that I did not ask for this information, it came, it will install. Okay. So, this is how you can alter the mapping between IIT Bombay's AC.in to Mallory's IP. Is this clear what is happening? Basically, through glue record you are giving the wrong mapping, which the user is now going to use, even though he did not ask for that mapping, but the local DNS server will install it, and then it will tell Bombay's IP address is this Mallory's IP address. Bombay's host name is Mallory's IP address. Okay. So, this happened, and thereby the solution people came up with is that you do not install someone else's domain's information. For example, if you ask for Delhi, this glue record better be related to Delhi, it cannot be Bombay's. So, you know the domain, right? Domain is iitd.ac.in is the domain. So, this is telling about iitb.ac.in, which is not part of that domain. So, DNS servers, the local DNS servers were added this extra information where they said you cannot install such a glue record, because there is no business of Delhi to tell what Bombay's things are. Okay. So, that is the solution to this specific issue thing. So, now let us see other types of attacks in DNS. So, let us start out with something called on path attacks, where this is the local DNS server which is trying to resolve some, let us say Amazon.com. It is trying to resolve, so it sent a request saying resolve this Amazon.com's IP address. Okay. Now, in response to this, some reply came which is saying this corresponds to this IP address. Now, because there is no authentication, if Mallory were to construct this reply and pass it, this local DNS server will install this entry. So, the challenge is for Mallory to construct the right reply. So, for this, what does Mallory need? If Mallory is on path means she can see the request basically. If she can see the request, in constructing the reply, what information does she need? She needs, again much like before, IP address, source will be, the source will be Amazon's authoritative name server, destination will be the local DNS server. Port also, you have to see what port was in the request, you have to reproduce the ports by flipping them, and in addition to that you need to also specify the ID, the correct ID to map the request to reply. If you are able to get this 5 pieces of information from the request, you can construct the reply and spoof. This is a spoofed reply, where within this, in the body, you can say Amazon.com's thing corresponds to Mallory's IP. So, this is a spoofed DNS reply which Mallory has constructed to trick the local DNS server. On path things are very straightforward, because you can see the request, you can easily assemble this. So, these attacks are not as interesting. The challenge is an off path attack. So, let us see how to do off path attacks. So, in this off path attack, as I mentioned, the source IP, source ports are straightforward, they are not that hard to predict. It is the ID that is a bit harder to predict, much like before. Okay? Now, let us assume that this local DNS server is doing sequential IDs. That is, if it sends one request, let us say it chose ID X, the next request will be X plus 1. Because it is sequential. Given this information, if you are not on path means you cannot see what the request is. Without seeing the request, can you construct a reply that will be accepted by the local DNS server? As I mentioned, as part of this reply, you need to get the IP and port information ready, but this is not hard. This is easy to figure out, but ID is slightly problematic. So, how can you solve this problem? So, again this is slightly tricky. I want to give it a shot. How contact, who will contact with what? I think you are on the right track, but you have to be a bit more clear. So, anyway, so what Mallory has to do is Mallory will first query this local DNS server saying resolve for me, let us say mallory.com. Okay. Now, this local DNS server in response to this is going to send a request with certain ID. Now, this request will go to Mallory's authoritative name server because it is Mallory's domain, and that Mallory's authoritative name server is under control of Mallory, and it will look at this, figure out what the ID is, and it knows that the next request this will send will have ID plus 1. So, now maybe it is now wants to maybe change some bank. So, it itself will say now resolve bank.com. Now, second request will go with ID plus 1. But because this guy already knows the ID, for this second request it will send a reply constructed correctly with the ID as ID plus 1 and saying bank.com's is Mallory's IP. Mallory is some other IP, need not be the earlier IP, some IP. Do you understand what happened here? Now, because this is, there is no authentication, it will act on it. ID matched, things are fine. It is now going to install this, and then through phishing coupled with that, you are now launched an attack. And you are not even on path, you are off path. You have not even seen the original request. But there is a challenge here in that this request, whatever you are sending out here, will also go to bank.com's authoritative name server, and that guy will also send a reply. So, there are two replies coming, one is coming from Mallory, one is coming from the right guy, and it is a question of who gets to local DNS server first. Once it installs, it will reject the other. So, there is a race against time here. So, this will only succeed if somehow Mallory is able to get to it faster than the other guy, especially if Mallory is part of the same local area network, it is not harder, that will take more time. So, this guy can easily inject. Okay. So, this is what is called off path attack. So, naturally earlier DNS implementations were using sequential IDs, they found out this attack. So, then the solution is naturally use random IDs. Okay. So, people used random IDs, and then this also somehow did not quite work out. Again, I won't get into too much detail, but I will just mention that there is something called birthday paradox. Have you heard? Anyone has heard of this birthday paradox? Basically, it tells that two people having the same birthday, that number is very small and it's quite surprising. Some very small number, whatever those many people are there, they'll have a same birthday. Okay, so that's the birthday paradox, where the idea here is you basically send many requests with different IDs. So basically, Mallory will bombard the local DNS server asking it to query, let's say this bank.com, query this, bank.com, query this, and somehow this local DNS server, the way DNS is implemented, it doesn't, again, these are all lazy implementations. We don't remember, oh, I already sent this DNS request, these are all duplicates, let me wait for the first to come before it doesn't do that. If it got a request, it will send out those requests. So if Mallory has asked this local DNS server to resolve bank.com's IP 1000 times, it will send out 1000 requests out, each with a different ID, because the ID is random. Is this clear what is happening? So you are basically saying resolve bank.com's IP address for me, and you are asking it to resolve it 1000 times. Then the local DNS server will send 1000 requests out with different random IDs. And leveraging this birthday paradox, where you are sending out all these requests, you will also send random replies with, of course, the port number, IP addresses matching, but IDs you will just guess, hoping one of them will match. So this guy has sent ID 1, ID 2, ID 3, whatever 1000 IDs. This here also you will send ID A, ID B, whatever ID C, and so on. If somehow 5 matched with X, you are done. Is this clear? ID is a 16-bit field. So you have 2 to the power of 16 options there. And people have shown that with as few as just 255 requests, there is a 50% chance you will get a match. It's not a very hard, 255 requests are not that much to generate, you just generate. Okay, this is clear. So this is leveraging the birthday paradox, where you have a lot of requests that are going out with random IDs. You also are randomly guessing the reply IDs, and if one request ID mapped with your reply ID, you are done. That guy will install it in the cache. But these also have a race against time. So there is something called Kameswari attack that prevents this race against Kameswari attack that prevents this race against time also, which again I don't want to get into, but this is one of the ways in which DNS farming can happen. Okay. So currently DNS again is a very important service, because without, if you break DNS, things are going to not work out. So the protection or the defense in these is one, is they have combined ID with a random source port. Okay, so this is 16 bits and port is another 16 bits, I think. Okay, so the space they have made it larger, so you cannot guess. So now you have to guess in the 2 to the power of 32 whatever space. Okay, so this is the only defense now against DNS, where when you send these requests out, not only do you choose a random ID, you also choose a random source port. Earlier you didn't choose random source port, it was a fixed port number corresponding to DNS. The destination port is still fixed to DNS port, but the source port varies now, which is random. Okay. So this is with respect to the, this is the current production, but because DNS is such an important service, people have incorporated a secure DNS protocol. They have designed the secure DNS protocol DNSSEC, but unfortunately it's been quite some time. Even now I think the coverage for this is only 10%. In other words, only 10% of all the mappings of host names to IP are covered with DNSSEC. It's still not as popular. It is catching up, but it's still not there. And DNSSEC uses certification using digital signatures basically to sign this host name to IP address mapping. It will sign. Some guy will sign it and thereby you trust it. So that's the mechanism behind DNSSEC. Again, I won't get into too much detail here. This is clear what is happening so far? Okay. So that is one application layer attack. Let me also talk about another application whatever attack, which is called the amplification attacks. These are used to launch DOS attacks. In fact, in the recent past, lot of DOS attacks are launched based on this amplification attacks. And again, this is a very interesting idea. Oftentimes, you provide services through certain machines. So, for example, there is this NTP, this is the time protocol. So, if you want to sync your machine's time, there are these servers that are out there. These are NTP servers, many of them will be there out there in the world. You can contact any of this server and sync your time. You will get global time then. Okay, so these are called NTP servers. You also have lot of DNS servers that are out there which will resolve things for you. You have to trust it, but Google itself has lot of DNS servers that it has installed. So these servers, when they are out there, you are now going to leverage these servers to launch a DOS attack on some victim. So let's say this victim is, suppose you want to launch an attack on Facebook.com. So that is the web server of Facebook. You want to bring it down. So what the attacker does is the attacker is going to contact each of these servers that are providing some service. Let's take the example of NTP. He is going to send out these requests, and these requests, let's assume that they are 10 bytes. They can be very small requests. So for this attacker to generate many of these requests with just 10 bytes, he doesn't need too much bandwidth. He can potentially whatever generate it and contact all of them. And when he contacts them, what he is going to do is, in the source IP address, he will use the victim's IP address, which is Facebook's. And the destination, of course, he will contact this NTP server 1. So he will generate one packet like this, another packet with the victims, again NTP server 2 and so on. Okay? And these are certain requests he is sending. The amplification comes into play where that this guy, when he replies, he is going to query such that this reply may be 10,000 bytes. So a 10 byte request will result in a 10,000 byte reply. That is the amplification. And this reply he is going to do, he is going to send it to this victim now. Whereas this attacker, this bandwidth, whatever is x, this bandwidth is going to be 1000x now. And it will overwhelm the network capacity of Facebook now. It can't cope with this bombardment of traffic. And you didn't, I mean, you just leveraged public servers for launching this attack. You wouldn't, I mean, you as an attacker hardly had any work. All you needed to do was generate this request and send them to some of these public servers, and the public servers are now bombarding the victim with a huge amount of traffic, which is 1000 times more than what you had to generate. Okay, so this is called an amplification attack, and people have achieved 1 Gbps all the way to even more than even terabits per second. they have bombarded certain organizations with this type of attack. So it's a very powerful attack where you are using this amplification to do it. So recent DOS attacks are all based on this amplification attacks. Okay. So with this we are done with the application layer attacks. Okay, I'll just maybe cover just 5-10 more minutes of firewalls, because they are there as part of the lab, and then we will break. So far what we have seen is that there are attacks at different layers of the protocol stack, and of course there are defenses. Some have no defenses. For example, those amplification attacks, if you launch them, there is no easy defense. So in fact that is what people leverage. You just try to put a filter, whatever it is, that's how you manage, but things are complicated in this space. So what we are going to look at is a specific defense mechanism which is based on firewalls, where the idea is, again this is something in real life also you must have seen. When you go to a mall or any other place, there are certain entry points where you put personnel so you don't put these personnel all around. So basically there is some exit and entry. At these points you put some defense in place, where they are going to examine things quite carefully and allow people in or out. So that's the basic idea. So firewalls do something similar in the networking space. So you have this organization, and there will be some router that is going to connect you to the outside world, and typically near this router you put a firewall which will track what are the packets that are coming in, what are the packets that are going out. And for example, if someone outside is trying to do some scanning, you can figure out whatever that IP address and block. Earlier I said, right, if you are seeing a TCP SYN flood attack coming from one specific IP address, you could put a firewall rule to say drop all packets from that particular IP address. Okay, this is a rule. Okay. Now within firewalls there are in fact three types of firewalls, but I will touch upon only two types, which is stateless and stateful. Stateless firewalls basically are going to look at a packet header, and just by looking at these fields, typically these are IP addresses, port number, these are the two main fields that they look at, and based on this they decide should I drop it or pass it, accept it. When we say stateless, they don't care what packets happened before, what packets are happening after. They just look at a very specific packet, look at its header and decide should I allow it or should I drop it. Those are called stateless firewalls. Stateful firewalls, in the other hand, keep state. They will say, okay, this packet came, which connection does it belong to? Did I allow that connection? Is that connection allowed or not? So here, for example, they will keep track of what is the SYN packet, did a SYNAC come? If a FIN happened, then that connection has been cleared out. Then if another packet for that connection comes when the connection has been cleared out, they won't allow, because that connection is not there anymore. Okay, so these are called stateful, which means they are maintaining some state about what are all the connections that are currently active and only packets of those connections. So basically stateful is at connection establishment time, they apply some rule to allow it or not. After this connection establishment, all the other packets, they will just check if the connection is there or not. If it is allowed, they will allow. If it is not allowed, they will drop. So there is some state that they maintain. So that is with respect to this. Now what you are going to see in the labs is something called IP tables. So this is again a Linux based command line, where at the user level you can type rules. which the kernel will execute. So, for example, you can type rules that say that, for example, on this port with this IP address you drop the packets. You can type such a command using IP tables, then it will drop all those packets. So, these IP tables basically access kernel modules. It will tell, the IP table will tell, go implement this rule, which a kernel module will implement based on whatever traffic is coming in or going out. Okay. So, for this you can specify these rules. These are called access control lists, ACLs, which are nothing but a bunch of rules which the firewall will implement. Typically these rules, there are certain tables, because it is called IP tables, there are certain tables called output table, NAT table, filter table, whatever. So, there are these type of things. Again, I do not want to get into the details of this. You will predominantly deal with output table. So, with that, whatever rules you put, it will allow, as in whatever packet is coming in or going out, it is going to drop or accept based on what rule you put. So, more of this you are going to see as part of the lab in the afternoon. I think that is about it. Yeah. Any questions before we break? Okay.